Oxidation states of first transition series. Why transition elements show variable oxidation states? The reason behind the variability of oxidation state in transition elements is that it is due to the presence of Ns and N-1 d electrons. Electrons from both the energy levels are used for the bond formation. This is because of very little difference in the energy levels of these orbitals. And the most common oxidation state for first transition series is +2. This is due to the loss of Ns2 electrons and also +3. In case of scandium, its electronic configuration, its atomic number is 21. Electronic configuration, outer shell 3d1 4s2. In +3 state, if it lost its all the 3 electrons, that is 1 electron from d orbital and 2 electrons from s orbital, it becomes argon 18, means noble gas configuration or stable configuration. In +2 state and in +3 state, means in lower oxidation states, transition elements form ionic compounds, and in higher oxidation states like +4, +5, +6 and +7, they form covalent bonds. In +2 and +3, they form ionic compounds, and in +5, +6, +7, they form covalent compounds. For example, in case of permanganate ion, manganese is present in +7 oxidation state. Here it is present in +7 oxidation state, and it forms covalent bond between manganese and oxygen. Means higher oxidation state, when the oxidation state increases, the covalent character increases and the ionic character decreases. In D block elements, the higher oxidation states are more stable for heavier elements. Higher oxidation states more stable for heavier elements. For example, molybdenum 6 in +6 oxidation state, tungsten in +6 oxidation state is more stable than chromium in +6 oxidation state, and this is the reason for chromium present as a dichromate in potassium dichromate, in which chromium is present in +6 oxidation state, which is a strong oxidizing agent K2Cr2O7, is a potassium dichromate, which is a stronger oxidizing agent in acidic medium than molybdenum trioxide and tungsten trioxide, which are mild oxidizing agents, and in these cases molybdenum is present in plus 6 oxidation state and tungsten is also present in plus 6 oxidation state. Here the difference is that the molybdenum and tungsten are present as a single atom in the compound, but in case of potassium dichromate the chromium is present as a diatom. It means molybdenum and tungsten are more stable in plus 6 oxidation state than chromium plus 6 oxidation state. Transition elements also show low oxidation states in some compounds or complexes, and these compounds are called as coordination compounds. For example, CuCl, in which copper is present in plus 1 oxidation state. Nickel tetracarbonyl nickel. This is a tetracarbonyl. CO is the carbonyl group and 4 represents the tetra. Tetracarbonyl nickel is also a coordination compound or a coordination complex in which nickel is present in zero oxidation state. Similarly, FeCO5 means pentacarbonyl iron, in which iron is present in zero oxidation state. It means transition metals or transition elements show low oxidation states in these compounds. The oxidation state of a metal in a solvent depends upon the nature of the solvent in which metal may undergo oxidation or reduction. For example, copper 1 positive. It is unstable in water because it undergoes oxidation in water and to form copper 2 positive. Copper 2 positive is stable in water. Similarly, Fe2 positive. It is unstable in aerated water. Aerated water means water containing air and undergoes oxidation to change into Fe3 positive. For example, as in case of rust, in which when iron comes in contact with oxygen and aerated oxygen or moisture, it changes from Fe2 positive to Fe3 positive and forms the rust. Oxidation state of transition metals depends on the nature of combining atoms. The compounds of metals with fluorine and oxygen exhibit the highest oxidation states because fluorine and oxygen have small size and high electronegativity, due to which they form different compounds with the transition metals. For example, CrF6, in which chromium is present in plus 6 oxidation state. Similarly, in case of oxides, Mn2O7, manganese is present in plus 7 oxidation states. It means when transition elements combine with fluorine and oxygen, they show variable oxidation states up to highest oxidation state, means from plus 2 to plus 7. Trends in properties of transition elements. First one is complex formation. Transition elements form number of complexes. This is due to the availability of vacant d orbitals and large charge by radius ratio of their metal ions. Charge by radius ratio means polarization, and polarization is a phenomenon in which when a positive charge or a cation approaches towards the negative anion, its electron cloud distorts and attracted towards the positive cation. And this distortion is called polarization of anion. And in case of transition elements, they have small size of their cations, means metal ions, due to which they have more tendency to show polarization. For example, K4FeCN6. It is a complex compound in which 6 Cn negative ions are attached with iron. Iron is the central atom here, and the Cn negative ions are called ligands. Due to the smaller size of Fe, iron, they form complex compound with the iron. And the name of this compound is potassium hexacyanoferrate. The name of this compound is potassium hexa means 6 ligands, hexacyano cn cyano ferrate Fe ferrate. Next is the interstitial compounds. Interstitial compounds in which the small atom occupies the interstitial sites to form an alloy, to form an interstitial compound. For example, suppose this is a crystal lattice of transition element. And these are the empty spaces or vacant spaces or interstitial sites. And the small atoms like hydrogen, carbon, boron, and nitrogen. They occupy these interstitial sites and form the interstitial compound. For example, titanium carbide, in which carbon is present in interstitial sites of titanium crystal. Similarly, for Fe3H, in which hydrogen is present as a in small atom in interstitial or vacant sites of iron crystal or iron lattice. Due to the presence of these small atoms, they form the compound very hard and rigid. They have high melting point due to their rigidness and hardness. They also show conductivity like that of pure metal, and they acquire chemical inertness, means they do not react with any chemicals. For example, in case of stainless steel, iron forms interstitial compound with carbon. This is the composition of steel, and the compound is called interstitial compound. Next is the alloy formation. Most of the atoms of transition elements form alloys with transition metals, and the atomic radii in this case do not differ by more than 15%, so that the host atoms are easily replaced by the other metal atoms. For example, in case of copper and brass and bronze, brass whose composition is copper plus zinc. Copper is the host metal atom and Zn is the foreign atom. And when Zn, zinc replaces the some of the copper from its crystal lattice and forms the alloy, because zinc has a comparable size with copper. Similarly, in case of bronze, copper plus tin. Here, copper is the host atom and tin is the foreign atom, which replaces some of the copper atoms from its crystal lattice and forms alloys. And the alloy called is bronze. Oxides of transition metals. Metals of first transition series form oxides with oxygen at high temperatures, and the oxides formed in the oxidation states of +1 to +7. For example, MnO, Mn3O4, Mn2O3, etc. These are some oxides of manganese, in which the oxidation state of manganese here in case of MnO is +2. In case of MnO, its oxidation state is +2. In case of MnO2, oxidation state is +4. And in Mn2O7, its oxidation state is +7. It means transition elements form compounds in oxidation states from +1 to +7, means they show variable oxidation states in their compounds. Next is the ionic character of oxides. As the oxidation state of manganese increases from +2 to +7, the ionic character decreases. Here, the oxidation state of manganese is +2. In this case, it is +8/3, and in Mn2O3, it is +3. MnO2 it is +4, and in Mn2O7 it is +7. When the oxidation state increases, the ionic character decreases, means tendency to lose electrons or transfer electrons decreases. Hence, the tendency to share electrons increases, means covalent character increases when the oxidation state increases, and the ionic character decreases when the oxidation state increases. Next is the acidic character. Acidic character increases when the oxidation state increases. And some of the oxides show amphoteric nature, like Mn2O3, MnO2, and Mn3O4. All these three show amphoteric nature, means they react with both acids and bases. And the acidic character from MnO to Mn2O7 increases when the oxidation state increases.